maybe some fine-grained sandstone, but there's a layer of good solid sandstone at the top. And it's at an angle. This is a cut and fill structure. This was a softer sediment here, and then the channel changed and the current came in and scoured away the sediment, cut a new channel, and then filled the channel with sandstone.
So you can see that.
Yeah.
I mean, how does it cut so perfectly?
Well, because when the water was there, when it was a channel, that was solid sediment and water, and that you don't go gradually from the sediment to the top to the sediment. Now, which way is up here? These beds are right side up, and you can demonstrate it very easily. Remember cross-cutting relations? The bed that cuts across is the one that's on top. That one up there is younger than the ones below, because the ones below here were already here to be cut off. So in this particular case, the rocks are not upside down. They're right side up. That isn't always the case. Our last stop, if we have time for it, we'll show a case where the beds are turned over upside down.
How is that possible?
It's a collision.
Oh, yeah, that's true.
And here, the beds are not that badly disturbed. They're folded, but you saw the fold. The fold was fairly open. The farther you get back towards where the collision takes place, the folds end up very tight and very steep, and some of them are turned over. If this is one bed here, beds down here are actually turned over. How do you tell that they're turned over? Because of things like cross bedding and cut and fill. It's the evidence that you have. Yes, you can see that it's turned over. There are other ways to do it also. I mentioned some of them to ripple marks, for example. Ripple marks, mud tracks, raindrop imprints, graded bedding.
Here it's slanted, but that's the way it is.
This was probably horizontal originally, and that one was tilted down in the channel. But now, of course, the stuff that was horizontal is folded.
Right.
Okay, if that's up on top, then as we keep going in this direction, if the rocks keep dipping in that direction, then we're going older and older, because the farther we go in that direction, the farther down the rocks are. And if we go in that direction, the rocks keep getting younger. The youngest rocks are up to the top of the hill, the road cut. And then the rocks are folded the other way, and we keep going and we get older again. So when you think about it, after I've been doing this for 60 years, and for me, I don't think about it.
Yeah, it's natural.
It's just the way it is. Now, a question. Are you about to ask one?
I was.
I'll bet it's what I was about to point out.
Wondering about the green and the gray.
That's exactly it. Yes, that was my point exactly. I was going to get to that. In fact, that's one of the reasons I stopped at this particular spot. Any idea why that might be the case? Obviously, it's not a single bed, because it's discontinuous, and you get isolated masses of green.
Does it only wash in during a storm?
It's the same rock. It's not a pebble or anything. It's the same rock, and you can actually follow beds right through the green. Okay, so any idea what it might be?
It's green.
How about, here's a hint. The color is from iron. And this is colored by hematite. There's a little bit of hematite in the rock. And as you know, powdered hematite is blood red. That's where the name comes from. But this isn't. This isn't hematite here. What is different about it?
There is some mica inside?
Maybe.
It's a little bit shiny.
Yeah, there are tiny grains of mica in there, yes.
What kind of rock is this?
That's a sedimentary mica though. That was deposited
So siltstone.
as tiny mica grains. Okay, here's the reason. Wherever you get this greening, there was some organic material, plant material. And plant material is carbon, of course. Carbon and carbon compounds. And it tends to suck oxygen away. So the hematite is iron plus 3. This has sucked some of the oxygen away, and the iron here is iron plus 2, which tends to be greenish minerals.
Oh, he's saying he's talking about.
So that's what's in here. It's the same original rock, but wherever the rock contained a little bit of organic material, it sucked the oxygen away from the iron.
It looks like paint.
Yeah, it is. It's completely natural, as you can tell by the fact that it tends to follow the bedding. Now, why you find the plant material here? That's in the finer material. Up here, it's a little coarser. Well, it was coarser because there was a little bit more current there, and the finer material was carried away. And of course, the plant material is very fine and light. So in the sandstone, you did not get the plant material deposited. It got carried further down, where the current was no current at all. There, the plant material settled into the mud and was available to grab all the oxygen and change the iron to +2 from +3. Now, this rock here is known as red beds, colloquially, for obvious reasons. It's reddish. If you go back 3 billion years in the Earth's history, there aren't any red beds. Why weren't there any red beds 3 billion years ago?
Oxygen.
No oxygen. The oxygen came in, remember I talked about banded iron formation? When all the iron +2 in the oceans, iron +2 is very soluble. Iron +3 is not. So when the oxygen came in, all the iron that had been dissolved in the ocean suddenly went down to the bottom. And that's where all the big iron deposits in the world come from. Now, there are younger deposits that are small, and there are places where deposits are even forming today, but they're very small. The really big ones are in that episode when the oxygen first entered the atmosphere. Here, the oxygen was removed by the plants, and so we're back to an oxygen-free environment right here.
And the
Here,
same with
no,
the.
here there's oxygen. Here there wasn't.
And it's the same with in the crevices here. That green.
That's a plant. That's lichen.
Ah, it's lichen.
Yeah, that's
That's
a green. That's a green plant.
What's going on
like
with
an
this?
acid
It's neither
surface.
red nor green. Has the white stripe and the little itty bitty crystals.
Yeah, and I have a sneaking suspicion that this isn't from right here.
You think this was carried in?
I do.
Looking for your acid.
Yes, I'm looking for my acid.
He's going to. That might be limestone. Might not be too.
I'm suspecting limestone, and I think my acid is in the car.
You can test.
Oh
it
no,
the next
here it
place.
is.
Yeah, hydrochloric acid.
Okay, let's.
Gonna see if it fizzes. Doesn't fizz much.
It
It might be dull enough. It
fizzes.
fizzes. So it's
No,
limestone.
this little vein right here, that could be calcite or it could be quartz. Since it's in limestone, I suspect that's a calcite vein. How can I tell?
really fizzes.
Quartz does not fizz.
Quartz does not fizz. Also, quartz is harder, and also quartz doesn't have a good cleavage. I can see cleavages on that. So that's why I strongly suspected that it
All
was
those little
calcite.
crystals
Limestone,
growing there, those calcite crystals.
The white.
I
Is that brown?
believe they
calcite,
are.
that's right.
However,
Don't know for sure. Yes, 'cause they
calcite
fizz.
anyone?
Yes, because they fizz.
but that didn't come from right here. This was carried in. Well, it was carried in to prevent erosion here in this little gully. It's local rock, though. We will see it further down. Okay, that's it.
Let me go fast.